Title: Rescaled Topological Entropy. Authors: E. Rego, A. Rojas, and X. Wen AGH, University of Science and Technology, Krakow, Poland. Hangzhou International Innovation Institute of Beihang University, Hangzhou, China. And LMIB, Institute of Artificial Intelligence and School of Mathematical Science, Beihang University, Beijing, China. The paper Rescaled Topological Entropy by Rego, Rojas, and Wen develops a new invariant for continuous time dynamical systems, defined by smooth vector fields on closed manifolds. This invariant, called rescaled topological entropy, extends the classical concept of topological entropy to settings where singularities play a significant dynamical role. The motivation behind this work arises from a long-standing paradox in dynamical systems theory. It is well known that any continuously differentiable vector field on a closed surface has zero topological entropy. Yet, some of these systems exhibit chaotic behavior, sensitive dependence on initial conditions, complex recurrence, and unpredictability. The classical entropy fails to detect such chaos because it measures orbit separation at a fixed spatial scale, without accounting for variations in the flow's velocity field. The authors ask a fundamental question: is there a notion of entropy capable of revealing chaotic features in flows on surfaces, especially those that have equilibrium points or regions where the velocity nearly vanishes? A second question concerns the relationship between entropy and periodic orbits. For expansive vector fields, it is known that the topological entropy provides an upper bound on the exponential growth rate of periodic orbits. However, this result relies heavily on uniform expansivity and the absence of singularities. The authors wonder whether a similar upper bound can be obtained for vector fields that are rescaling expansive. That is, expansive once the natural speed of the flow is taken into account. To answer these two questions, they introduce a new invariant, the rescaled topological entropy. Topological. This quantity is assigned to every continuously differentiable vector field on a closed manifold, and satisfies 6 fundamental properties. It is non-negative. It bounds from above the classical topological entropy. It coincides with it in the absence of singularities. It is positive for some surface vector fields. It is invariant under rescaled topological conjugacies, and it controls the exponential growth rate of periodic orbits in rescaling expansive flows, whose singular sets are dynamically isolated. Let us begin by recalling the context. A vector field on a closed manifold generates a flow, a one-parameter family of transformations describing how points move under the system. Topological entropy, in the classical sense, measures the exponential rate at which distinct orbits become distinguishable as time increases. In discrete systems, it counts how many orbit segments are needed to cover the phase space at a given resolution. For continuous systems, the same concept applies to the time-one map of the flow. However, when the flow has singularities, points where the vector field vanishes, the traditional metric used to define entropy becomes degenerate. Orbits may spend arbitrarily long times near equilibria, and the distance between nearby trajectories may shrink to zero simply because the flow slows down. This produces artificially low entropy values, even when the system's geometry is highly complex. The idea of the paper is to compensate for this effect by rescaling distances according to the local magnitude of the vector field. Instead of comparing two trajectories directly, the authors divide their instantaneous separation by the speed of the flow at that point. In this way, slow regions are amplified and fast regions are compressed, balancing the geometric information across the entire manifold. This rescaling introduces a new family of dynamical distances, called rescaled metrics. Using them, the authors define rescaled dynamical balls and rescaled spanning sets in the same spirit as Bowen's classical construction of entropy. For a given time and a given tolerance, a rescaled spanning set is a finite collection of points whose rescaled dynamical neighborhoods cover the manifold, except possibly near singularities where the speed vanishes. By measuring the minimal cardinality of such sets as time grows, and taking the appropriate limits, the authors define the rescaled topological entropy of the vector field. This number quantifies the exponential complexity of the system after correcting for variations in flow speed. The paper then establishes several equivalent definitions of this invariant. It can be expressed either through covering numbers, separating sets, or local versions restricted to compact subsets away from singularities. Each formulation provides different technical advantages for proofs and estimates. A key step is to show that the rescaled entropy is always finite. The authors achieve this by bounding it in terms of the Lipschitz constant of the vector field and the dimension of the manifold. Thus, for smooth flows on compact spaces, the rescaled entropy provides a well-defined, finite measure of dynamical complexity. To understand when this entropy is positive, the paper presents a characterization similar to that known for classical entropy. Positivity occurs precisely when there exist compact subsets and sequences of times where exponentially many orbit segments remain uniformly separated under the rescaled metric. This means that the system generates exponentially growing distinguishable patterns, even when ordinary distances might shrink because of vanishing velocity. This characterization plays a crucial role in the examples. It explains how surface vector fields, which always have zero classical entropy, can nonetheless exhibit positive rescaled entropy due to the presence of singularities. The authors construct an explicit example on the two torus to demonstrate this phenomenon. The example begins with a simple periodic flow on the torus, represented by constant motion in the horizontal direction. This system has zero entropy. Then, the authors introduce a smooth modulation of the vector field that reverses the flow direction near certain vertical lines and introduces two vertical lines of equilibria where the velocity vanishes. The flow slows down exponentially near those lines, creating regions of very low speed. When analyzed under the classical metric, this slowdown suppresses orbit separation and drives the entropy to zero. However, under the rescaled metric, these regions are magnified, and the system reveals an exponential number of distinguishable orbits over time. As a result, the rescaled topological entropy becomes positive. This example illustrates the central idea. The new invariant captures the true geometrical complexity of the flow independently of how fast or slow it moves. It detects chaotic patterns that the traditional definition overlooks. The authors also show that this new entropy behaves naturally with respect to rescaled topological conjugacies. If two vector fields are related by a homeomorphism that respects the rescaled distances and carries orbits of one system to orbits of the other, their rescaled entropies coincide. This invariance ensures that the quantity depends only on the qualitative dynamics of the flow, not on specific coordinate choices or reparameterizations. Another major application of rescaled topological entropy concerns the growth of periodic orbits. For classical expansive systems, Bowen and Walters proved that the number of periodic orbits with period less than a given time grows at most exponentially, with the topological entropy as an upper bound for the growth rate. The authors generalized this result to rescaling expansive flows. They prove that if the singular set is dynamically isolated, then the number of periodic orbits grows at most, with an exponential rate bounded by the rescaled topological entropy. This shows that the new entropy retains the predictive power of the classical one, even in the presence of equilibria. The proof uses a detailed analysis of separating sets and a careful adaptation of Bowen-Apau's combinatorial arguments to the rescaled setting. It establishes a quantitative link between the speed-corrected orbit structure and the abundance of periodic motions. In particular, this provides a positive answer to the question of whether an inequality similar to Bowen's holds for vector fields that are almost expansive after rescaling. The authors also consider the class of K-star expansive vector fields, a well-studied generalization of expansivity introduced by Komuro. Since every K-star expansive flow is rescaling expansive, the previous results apply directly. As a corollary, any such vector field on a closed manifold with dynamically isolated singularities satisfies the same exponential bound for periodic orbit growth. Furthermore, by applying the Kupka-Smale theorem, which ensures that generic vector fields have only hyperbolic singularities, the authors extend this result to generic rescaling expansive flows. The paper is carefully organized into 4 main sections. After the introduction, the second section defines the rescaled topological entropy in detail and provides several equivalent formulations. The third section develops the concept of rescaled metric entropy, a measure-theoretic analog, and proves a half-variational principle establishing that the metric version is always bounded above by the topological one. The fourth section contains the proofs of all the main properties and presents explicit examples of systems with positive rescaled entropy. Let us look more closely at the measure-theoretic aspect. In classical entropy theory, one distinguishes between metric and topological entropy, the former depending on an invariant measure. The authors adapt this to the rescaled setting by defining a rescaled metric entropy, which measures the average exponential complexity with respect to a given Borel probability measure that avoids the singular set. They show that this quantity is always less than or equal to the rescaled topological entropy. This relation forms a half-variational principle, mirroring the standard one but avoiding difficulties caused by vanishing speeds. It also provides a useful tool for estimating rescaled entropy in practical situations where invariant measures are known. An important part of the work is devoted to proving that the definition of rescaled entropy is consistent and finite. The authors demonstrate that the rescaled entropy can be bounded above by a constant proportional to the Lipschitz constant of the vector field and the dimension of the manifold. This ensures that even when the flow slows down near singularities, the rescaled measure of complexity cannot diverge. The paper also establishes conditions guaranteeing positive rescaled entropy. The existence of sequences of sets with exponentially many points remaining uniformly separated in the rescaled metric is equivalent to positivity. This characterization allows the authors to construct explicit examples where the rescaled entropy is strictly positive, despite classical entropy being zero. Beyond the torus example, the authors build a second, more natural example on the two-sphere. They start from a smooth vector field whose flow moves vertically from the north to the south pole, slowing down near the poles but never reversing direction. Then, by carefully modifying the function controlling the vertical speed, they introduce two parallel circles of equilibria and regions where trajectories spend longer and longer times. Through this construction, the rescaled entropy becomes positive. The example also shows that positive rescaled entropy can appear robustly. Small, smooth perturbations of the vector field preserve this property. Thus, the phenomenon is not exceptional, but structurally stable under small changes. In both examples, the singularities play an essential role. They create slow zones where orbits linger for long times, producing a complex pattern of approach and departure that, when analyzed in rescaled units, reveals exponential complexity. The ordinary entropy, insensitive to these variations in speed, would completely miss this behavior. The authors then discuss the invariance of the new entropy under rescaled topological conjugacy. This means that if two vector fields are related by a homeomorphism that distorts distances in a controlled way respecting the local speed, their rescaled entropies are identical. Such invariance is crucial because it confirms that the new invariant depends only on the qualitative structure of the flow and not on particular parametrizations of time or coordinates. In proving the link between rescaled entropy and periodic orbit growth, the authors adapt techniques from classical symbolic dynamics to the continuous setting. They construct rescaled separating sets associated with periodic orbits and show that their cardinality bounds the number of distinct periodic trajectories. Combining this with the entropy definition yields the desired inequality connecting growth rate and entropy. This result generalizes a central theme in entropy theory. Entropy governs the exponential proliferation of periodic orbits. The paper ends with a discussion of how the results fit into the broader study of entropy for flows with singularities. Traditional topological entropy fails to capture much of the complexity in such systems, because it treats time uniformly, ignoring that near singularities, the effective timescale of the flow changes dramatically. The rescaled approach proposed here corrects that imbalance by adapting the metric to the natural local speed of the flow. In doing so, it restores the connection between entropy, expansivity, and orbit growth that is lost in the classical setting. From a conceptual viewpoint, this research unifies several themes in modern dynamics. It bridges the gap between topological and metric definitions of complexity, incorporates the geometric structure of vector fields into the entropy framework, and introduces a rescaling mechanism that preserves dynamical invariance while resolving the degeneracies created by singularities. The resulting invariant behaves naturally under smooth deformations, is stable under topological conjugacies adapted to rescaling, and extends the range of applicability of entropy theory to flows that were previously considered non-chaotic. The authors conclude by acknowledging that their constructed examples are somewhat artificial in appearance, designed primarily to illustrate the concepts. Nevertheless, they emphasize that the method is general and can be applied to construct smooth vector fields with positive rescaled entropy on many manifolds, including the sphere. They also suggest that further work could explore the relationship between rescaled entropy and physical observables, such as Lyapunov exponents, invariant measures, or fractal dimensions of invariant sets. The paper's mathematical rigor is complemented by its conceptual clarity. It not only defines a new quantity, but establishes a full theoretical framework for its study. Definitions, equivalent formulations, variational principles, invariance properties, examples, and applications to periodic orbit theory. This makes rescaled topological entropy a powerful addition to the modern theory of dynamical systems, providing insight into systems where time and space scales interact in non-trivial ways. In practical terms, rescaled topological entropy can be seen as a bridge between classical topological dynamics and the study of singular flows such as those appearing in fluid mechanics, celestial mechanics, or models of physical fields with equilibrium states. It offers a new lens through which the complexity of such systems can be measured, capturing the underlying geometric chaos even when the flow appears slow or degenerate in the classical sense. Finally, the authors acknowledge financial support from the National Natural Science Foundation of China and the European Union, Marie Sklodowska-Curie project. Their collaboration brings together ideas from differential geometry, dynamical systems, and entropy theory, resulting in a unified framework that extends the frontier of how dynamical complexity can be quantified. In summary, the notion of rescaled topological entropy represents a significant conceptual and technical advance. It refines the measurement of complexity in flows by integrating the geometry of the vector field into the definition of entropy itself. It aligns with classical results when singularities are absent, yet reveals hidden chaotic structures when they are present. Through rigorous proofs and explicit examples, Rego, Rojas, and Wen demonstrate that even smooth flows on simple surfaces can exhibit positive rescaled entropy, challenging the conventional wisdom that all surface flows are dynamically trivial from the entropic viewpoint. The paper thus closes a long-standing gap in the theory of dynamical systems, providing a new invariant that detects and quantifies chaos in continuous time systems with singularities. Its implications reach beyond topology and analysis, offering a refined mathematical language for understanding complexity, wherever time, geometry, and motion intertwine. Thanks for watching.